Our first student presentation is from the Aerospace Engineering Department and is titled Dreamed, Designed, and Built. And now, here is their project abstract. BroncoSat-1 is a trailblazing cube satellite technology demonstration mission, and a truly historic endeavor is our university's first space mission. Bronco Space's flagship program, BroncoSat-1, is a small satellite scheduled for launch into low Earth orbit on a SpaceX Falcon 9 in mid-2021. Once launched, this satellite shall be a landmark proof of concept in demonstrating the use of a dedicated and commercial off-the-shelf platform for artificial intelligence and machine learning in the new space industry. I now invite the aerospace engineering team to share their presentation.
Hello, everyone, and thank you, Alexis, for that introduction. My name is Michael Pham. I am the chief engineer on BroncoSat-1 and a third-year aerospace engineering student here at Cal Poly Pomona. It's an honor today to present to you Cal Poly Pomona's first space mission. Next slide, please. I'd like to begin by acknowledging that we only have 5 presenters here today, but it took an undergraduate team of approximately 35 students over the last 10 months to design the ground-up infrastructure for our first space mission. In the image you see here on this purple plate, you see the names of most of the students that have worked on this project. This is the top plate that will actually be traveling to space to immortalize all of the hard efforts that the students have put in throughout this project. And of course, I would also like to acknowledge that in the delivery of this mission, Cal Poly Pomona will be joining a very exclusive club of other universities worldwide who have successfully delivered a space vehicle for flight. Next slide, please. As was mentioned in the abstract, BroncoSat-1 is a 1.5U CubeSat that will be in a 525 kilometer sun-synchronous orbit, and we're expecting the mission to last approximately 2 years, but it could last longer. This will be a trailblazing demonstration for the use of artificial intelligence and machine learning in low Earth orbit, and we're hoping that the demonstration done here will enable advanced operations in Earth observing, swarm observations, and scientific investigations that were never before possible in the space industry. And probably most importantly, this is going to be the first time that Cal Poly Pomona has delivered spaceflight hardware. And I think something that I should mention is that these small satellites are in fact incredibly small. You see here a picture of BroncoSat-1. And if you have a 500 milliliter water bottle around you, it is only slightly taller than a 500 milliliter water bottle. Next slide, please.
Hi, I am Katina Orozco, and I am one of the main electrical engineers who worked on integration for BroncoSat-1. On this slide, we will be talking about the subsystems that went into making up BroncoSat-1. As you can see here, we have 5 main subsystems, that being the communications, the electrical power, payload, our attitude, termination and control systems, and the main flight computer. I myself got to work on a majority of these subsystems as I hand soldered a majority of the wiring harness for the satellite. And all of these subsystems were validated with hardware in the loop tests, which took place over the past couple months. Next slide, please.
Hello, everyone. I'm Christopher Artates. I am the Chief Electrical Engineer for the BroncoSat-1 project and a computer engineering major. On the slide here, you could actually see some custom designed hardware that we have used in BroncoSat-1. These encompass at least four of the 5 subsystems on BroncoSat-1 that have all been designed and assembled and tested with all of those extensive hardware in the loop testing. So on the left, you could actually see these PCB boards, these printed circuit boards, starting with the solar panels that are the green boards on the left, the battery board in the center, the top plate that Michael had mentioned earlier with all of the most of the names of the team on that PCB board, and on the bottom you could see a bunch of adapter boards that we had to use to connect everything together. Next slide, please. On this slide, we actually see a custom flight computer board that we have adapted based off of a flight computer that was designed by Stanford University's Rex Lab, and that computer was called the PolyCubed. Now, for BroncoSat-1, we have we had to add additional functionality to that flight computer to address the needs for the mission, specifically addressing attitude determination and control. So we will talk about that later on in the presentation, but we've added secondary IMUs, sun sensors, and magnetorquer drivers. And because of this comprehensive design, we've actually had to we wanted to rename the computer from the PyCubed to the PolyCubed in honor of this being Cal Poly Pomona's first ever space mission. Next slide, please. So now the key part of the mission is our payload, and BroncoSat-1 is actually a technology demonstrator mission. Now the technology that we are demonstrating is the NVIDIA Jetson single board computer that you could see in the image on the right. Now the most novel qualities of this computer is that it is a ARM-based Linux computer similar to a Raspberry Pi, but with a desktop class graphics processor. And the NVIDIA Jetson platform has never been used in a satellite before. As far as we are aware, this will be the first known space flight of the NVIDIA Jetson. And without knowing how it would behave once it is in low Earth orbit, the BroncoSat-1 team has spent months extensively testing the entire satellite in various extreme conditions, such as near vacuum or super frigid temperatures, and verifying that all the subsystems work together with those hardware-in-the-loop testing. Now, in the next slide, my colleague Max will actually talk about how we use the NVIDIA Jetson. Next slide.
Hello, I'm Max Romano-Smith, computer science student, and I'm the software payload lead for the mission. As mentioned, this is a technology demonstration of AI, and as such, we have a series of benchmarks that we have selected to run on our NVIDIA Jetson. In these benchmarks, we have two custom benchmarks that our team wrote ourselves, a general image compression to test possible compression before downlink, as well as an edge detection to test parallelization in general. Along with these, we have a series of industry standard NVIDIA benchmarks that share common architectures to other image recognition and other possible recognition algorithms that may be used in future missions. Next slide, please. So one of our custom benchmarks is this edge detection. This uses the SOBAL algorithm. And the main reason we threw this on here is it's a very easy to parallelize algorithm. So in doing so, by having it run on a single core processor and a single thread, it takes approximately 10 minutes to perform the edge detection shown on this slide. However, with parallelization, we're able to speed this up to about 10 milliseconds. So we want to confirm that this functionality stays true in low Earth orbit. Next slide. And in showcasing one of the industry standard models that we're demonstrating, we're running the You Only Look Once model. The key for this one is it performs image recognition off of a single frame, allowing to detect and track multiple possible inferences all at the same time, and is useful for running on video recognition. Part of the idea of this one is, again, to test image recognition and tracking in future missions. Along with our AI, we have another suite of software that my colleague Mateo will be talking about in the next slide. Next slide, please.
Thank you, Max. Hello, everybody. I'm Mateo Gironda, a mechanical engineering student, and I'm the control system lead for BroncoSat-1. Our communication system has a requirement of 2 RPM to actually be able to downlink effectively to our ground station, meaning that the satellite needs to be spinning slower than 2 revolutions per minute. To do this, we have actuators and sensors on board that use the B-dot algorithm to detumble any initial angular rate that the satellite might have to a slow enough rate so that we ensure stable communications with the satellite. We spent the first half of the development of the project actually simulating and validating the B-dot control system loop in MATLAB and Simulink through our simulations. And then if we go to the next slide, we actually validated the validity of the algorithm with hardware in the loop testing in a custom-made 8X test bed, which I'm going to let Catherine go over.
Hi. So in addition to building a satellite, the students all working on BroncoSat-1 have also developed our own equipment for both assembling and testing our satellite. Here we have our 8X controls system test. We're doing that with a 3-axis Helmholtz coil and a mass balancing assembly system that we also called Nano. So with the Helmholtz gauge, we are able to simulate Earth's magnetic field And in doing that, we are able to test our ADAC system by running our magnetorquer code and seeing how it interacts with the magnetic fields on the Helmholtz cage. And next, I will be passing it off to Michael. So next slide, please.
Thank you, Catherine. So I'm actually pretty excited because we just got these images through the legal department just a couple hours before this presentation. And one thing that I really want to nail down is the incredible fact that this entire space mission has gone end to end, from a clean sheet design to delivery in just over 10 months to the day since the project began last summer. And so the images you see here are of us actually delivering the spacecraft to our launch provider. And you can see in the images that the satellite is being placed inside of the pod that will take BroncoSat-1 to the Falcon 9. It will be loaded onto the Falcon 9, and then it will be taken to low Earth orbit in just under 2 months' time. And so this is a really incredible occasion for the students to be a part of. And on the next slide, please. I also want to highlight the fact that as a project that began and progressed throughout the pandemic, we started as a kitchen table and garage satellite project. And thanks to the incredible help we've received from the College of Engineering and professors here at Cal Poly Pomona, we've gone from garage and kitchen table satellite to being one of the few undergraduate research groups able to work on campus. And then finally, just later this summer, we will be actually flying to space and hopefully hearing back from our satellite in good order. And with that, 12 minutes is not a lot of time to discuss a space mission. So if any of you are interested in contacting us further, I've noted some emails here on the bottom, but I'm sure that Alexis can also put any members of the audience in touch with us if you'd like to learn more. So thank you everyone for your time. This has been a project that was dreamed, designed, and built by students at Cal Poly Pomona. And now we're just looking forward to launch day. Thank you.
Thank you, aerospace engineering team. We will now take a short break from speaking.